If you are speaking, probably you are muted.
Okay. Yeah. Okay, I think I can begin next.
Yes.
Okay. Okay, so to recap on the previous hour of the lecture, we have talked about the general overview of satellite quantum communications and how it places within the quantum network. We've talked about the atmospheric effect, namely turbulence and beam wandering, and the transmittance of the atmosphere. And we've talked about some of the difficulties of the optical link, such as diffraction losses being the most dominant loss that we have within our satellite, within our optical link. We've talked about pointing losses that arise not only because of the beam wandering, but also because of the fast, or rather is limited by the fast steering systems that we can have on our ground station and our satellite. And we've talked about the size of the receiving optics and how that plays into our link budget. Okay, so I think for the next hour, I will just finish up the anatomy of the satellite quantum communication mission. So the last part would be the detectors, right? Because if we are performing experiments in weak coherent pulses, then we will need single photon detectors. And likewise, if we are performing experiments in entangle-based QKDs, we also need single photon detectors. And the figures of merit that we need to take into account are detection efficiency, recovery time, technical noise that arises from dark counts, readout, and timing jitter, and swap considerations, meaning size, weight, and power. So over here, I have a high-level overview of some of the detectors that are commonly used in the telecom wavelength. And we have four major ones, and that is SNSPDs, so superconducting nanowire single photon detectors, SPADs, so single photon avalanche photodiodes, PMTs, and TES, so photomultiplier tubes and transition edge sensors. So PMTs and TES are pretty deprecated, so they're not widely used, but there are research groups working on single photon photomultiplier tubes, particularly those working on photo resolving single photon detectors. So the two main candidates would be SNSPDs and single photon avalanche photodiodes, right? So SNSPDs tend to have the best efficiency, the lowest timing jitter, the lowest dark count, and the highest max count rate, right? So I have some photos of single photon detectors that are commonly used in experiments like ours. And on the left and on the far right, we have two single photon avalanche photodiodes, right? The silicon based and the in-gas, in-P based APDs, right? So these two APDs operate at different wavelengths. So silicon-based APDs are suitable for optical wavelengths, so 400 to 800 nanometers wavelengths. And NRR, rather near-infrared, are more like in-gas APDs are better for telecommunication wavelengths. So one of the key difficulties in scaling up the wavelengths, such as using those in telecom wavelengths like 1550, is we are limited by the fact that in-gas-based APDs tend to have will always have higher dark count rates and lower detection efficiency than silicon-based APDs, right? So silicon-based APDs are starting to get more mature, that they can manufacture APDs that have much lower dark count rate, so 25 hertz. The best sort of single photon detectors that we can get are those such as the SNSPD system, like this one from ID Quantique. They are ultra low dark count, so fewer than 1 hertz, and they're suitable for a large range of optical wavelengths and near-infrared wavelengths. So in principle, can support experiments in the near-infrared region, like telecom region, right? The only issue with SNSPD systems is that they require substantial infrastructure, like cryostats infrastructure, because they need active cooling to ensure that the nanowires stay in its superconducting state, right? So clearly, detectors like SNSPD systems do not belong on satellites, but that may change with better. That may change at some point in the future. We never know, but at the moment, most of the APDs or most of the single photon detectors that we use on board satellites will be some form of avalanche photodiode, either silicon-based or in-gas based, right? One thing about single photon detectors is that because APDs that are based on silicon and in-gas will exist in sort of in orbit, they will degrade with gamma radiation exposure. So the radiation that you will observe when you are in orbit, right? So the diagram here is actually the avalanche the characteristic dark counts of the avalanche photodiodes, right? With increasing temperature, with increasing temperatures, right? So at higher temperatures, we will see a higher dark count rates because electrons get promoted because of thermal noise. But over time, they accrue radiation damage. So if you compare the dark count trends for APD2 at day 719 and day 27, you can see a substantial increase of dark count rates by several orders, right? Sorry, by at least an order. So this data comes from some experiments that we have done on APDs that exist in oh, of course, yeah. Thank you so much for pointing that out. Let me see. Okay. Point options and laser pointer. Okay, thank you very much. So these diagrams represent the dark count trends for APDs on board a satellite QKD mission that we have done in 2019. And we can see that with time, so with more orbits, with more days, if you compare the day 719 and day 27, we can see a substantial increase in count rates by a few hundred hertz, few hundred counts per second, right? And this is sort of, we cannot really do anything about the degradation of the material due to radiation damage, because there's only so much shielding that we can put on our single photon detectors before it eats into our budget. But what can, in principle, happen is we can reverse this radiation damage by in situ thermal annealing. So this is a research initiative that was done on the ground with our group. And what we did was that we repeatedly heated up the detectors to like 50 degrees Celsius. And then we cool it down using the thermoelectric coolers. And we see that we can actually reverse the radiation damage on the APDs. And further results from another experiment that is currently being done at the University of Illinois shows even better dark count rates, or rather lower dark count rates after annealing that is done in situ, in orbit. So at this juncture, and click with the laser pointer, sorry. Sorry. Okay, so now we can move on. So now that we have sort of gone through the anatomy of a quantum experiment, we can start doing a small overview of some of the experimental efforts that were done towards satellite quantum communications. So this idea of satellite quantum communications first materialized in 2002, but was first shown in the seminal work done by Michias at the team at the University of Science and Technology in China back in 2016. So they had this initiative where they launched a primary payload of entangled photon sources, as well as BB84 quantum payloads on board the Michias satellite, right? So this was launched back in 2016. It had a size of 600, it had a weight of about 631 kilograms, and is in sun-synchronous orbit. So its inclination is about 97.4 degrees, right? They also had some other secondary payloads that are not so very relevant, but the Michias satellite sought out to prove that we can perform a quantum key distribution experiment using decoy state BB84, and that we can create entangled photon sources that can survive radiation damage, the exposure to very large thermal differentials, and also survive launch into orbit, right? So they performed they performed a BB-84 using a decoy state BB-84 on this very compact, at least for the time, a very compact satellite of only several meters long, right? And the satellite and the quantum payload weighed only about 27 kilograms and drawing a peak power of about 2 point something watts, right? So they performed BB-84 protocol, decoy state BB-84 protocol, and their source was similar to the one presented earlier with 4 V-cell arrays, and they also had a detector module as well, right? And what they actually showed was that they were able to perform a decoy state BB-84 protocol with a significant level of key rate that is, or rather with a very high repetition rate. But the one thing that I would like to talk about is how they designed the timing and synchronization and the beacon laser. So within the QKT transmitter, a co-aligned beacon with a Q switch laser source that can be used to synchronize the timing between the satellite and the ground station up to 1 nanosecond. And additional lasers are also being sent to perform pointing and tracking using beacon laser and spot tracking. So the ground station was located at Dilingha ground station. So they used a 1 meter telescope and is located in a very mountainous area, about 3,000 meters above sea level. And that is very beneficial because it's somewhere that has very low sort of light pollution. And the fact that it's very high above ground means that they don't suffer as much atmospheric turbulence, right? So turbulence that arises because of traffic and urban activities. Their receiver module is also very interesting. So what they use is a compensation module, polarization compensation module, and they performed an experiment, or they performed a measurement using 4 single photon detectors on the 4 relevant bases, so HV and DA. And with this, they were able to generate a secret key rate that is several kilobits per second, right? So throughout the entire pass, we see this kind of increasing trajectory and decreasing trajectory, and that is because of the distance of the satellite as it passes through the optical ground station. So the range rate actually increases and decreases. When it's further away, the range rate is much higher, and therefore encounter a lower extent of secret key rate. And when it passes directly overhead, or as much directly overhead as possible, they encounter the highest level of key rate. So they successfully performed decoy state BB-84 protocols over the course of 2 years and successfully demonstrated that without the need for an active polarization manipulation, they can perform a high rate DS BB-84 with quite low quantum bit error rate. So that was one of the primary missions that they set out to do. But the second set of experiments that they set out to do was actually to demonstrate entanglement distribution. So they have this palm laser onto a PBKTP crystal in a Sagnac interferometer, and they can show that using this, that they can establish an entanglement distribution between 2 distant optical ground stations, roughly 1,200 kilometers away from one another. However, their entire architecture was very heavy, very swap dependent, or rather was very power intensive. And at the distance, at the attenuation that they have gotten, they weren't able to form a secret key towards entanglement distribution. So in the next sort of iteration of satellite quantum communication mission comes in the form of miniaturizing entangled photon sources, right? So this was done back in the day with Professor Alexander Ling, where he had this mission called Spooky One, and it demonstrated a compact and low power entangled photon source that existed on space. So they used a 3U CubeSat platform, which is about 30 centimeters across and 10 centimeters on its side. So it's like a small cube. And they show that with only a peak power of 2.5 watts, they can generate a very high fidelity entanglement, with a co-aligned BBO crystal using a type 1 SPDC process, right? So the benefit of this is that it is very temperature insensitive, and because BBO can be, or rather we don't use periodically pulled PPKTP, you can manufacture the crystals to be larger, and so they have a larger aperture. So it keeps the alignment the alignment is much less sensitive compared to a PPKTP crystal. So with this, paved the way to build miniature photon sources on a CubeSat platform. And this is quite important because in the future, if we want to have constellations of entangled photons, or rather constellations of satellite QKD networks, then we will need to scale down the cost of sending satellites into space. And the way you do that is by miniaturizing it, by making it as small and compact as possible. So CubeSats such as this can perform things like what we call piggybacking. Instead of sending a rocket to push out one satellite, we can actually send a rocket to send multiple CubeSats. And this is in fact what we do as a cost-saving initiative. So in this case, I believe we use JAXA, so the Japanese Space Agency's mission to send a few CubeSats onto space. And the current iterations, we also use services like Starlink and SpaceX to launch CubeSats for QKD missions at a very cost-effective price range, right? So in this year, the Chinese team, the one responsible for missions, also launched a microsatellite platform. So this is a current effort to demonstrate QKD, or satellite quantum communications, on a more compact platform. So they used a 20 centimeter aperture, and I think the total length of this was, so let me just use the laser. Right. So the total length of this was only about 1 meter by half a meter, and it only weighed about 94 kilograms. And they used an updated version of a decoy state QKD payload that uses a V-cell array, similar to the one that was shown previously, so that it does not require 8 diodes to perform this experiment. So you do have other communications laser diode in 812, and that is for timing and synchronization and for beacon tracking, right? So this actually made the QKD module much more compact and much more power efficient. Instead of having to drive 8 laser diodes, they only have to drive 1 laser diode. And this was recent, I believe, in March of this year. Okay, so another update that they have made was to significantly reduce the size of the optical ground station by employing portable optical ground stations. So these in total weigh about 100 kilograms and can be deployed in less than an hour. And what they found was that they were able to perform DB84 decoy state in many environments. So I highlight a few in urban environments and mountainous environments without much degradation towards the secret key rate. So their final keys range in the several hundreds of kilobits up to a megabit in 20th October 2024, right? So this experiment actually occurred in tandem with many other planned missions of compact QKD satellites, because you can imagine that having a low-cost QKD network, right, can actually enable more innovation and faster execution because of the lower overhead required. Because of that, there have been quite a few emerging QKD on nanosatellite platforms. So this include platforms like CubeSats and microsatellites. So there are 4 here that I would like to highlight, but this is non-extensive. We have an uplink. Just open up pointer. We have an uplink satellite, uplink quantum receiver in Canada due for launch in 2026. We have the ROCS, which was due for launch in 2025, but I believe is delayed. And we have these 2, which are due for launch, and this one is due for launch in 2025, and this one about 18 months later, right? So this is actually a satellite that was made by a spin-off company by those people who worked on Spooky 1. So we worked very closely with them to support their quantum experiments in space. So I want to talk a bit about the spectral, this one, the one in the red box, because this is the experiment that we are currently working on. And I'll try my best to dive as deep as possible as I can to sort of, give to wrap up clearly what what this lecture has been about. So the operational plan is that there are in total 4 links, right? A beacon laser at 685 nanometers, and this laser is used as a way for us to refer to the polarization. So it sets the polarization reference so that we can correct for it. As we say, the satellite will sort of like slightly torque and then turn as we pass, as the satellite orbits. And we have 2 780 links. One is a quantum link, passing down a 780 nanometer source, 780 nanometer photons with type 2 non-critical phase match BBO crystals. And we have another 780 nanometer link that is meant for timing synchronization. So what this is a Q switch laser with a high repetition rate so that we can use this to gate our detectors, right? So we get our detectors to reduce its exposure to the background, thereby reducing the effective background count. And from the main telescope, we have a 915 nanometer uplink, and this also aids in fine pointing as well. So the thing about pointing is that not only must the OGS point towards the telescope, not only must the optical ground station point towards the satellite must also point itself towards the optical ground station. And this is done by reaction wheels on the CubeSat. So reaction wheels are just wheels that can shift the momentum of the CubeSat so that it can orient itself such that we can perform the experiment. So we can perform the experiment with a high degree of pointing, right? So to support that, we actually built an optical ground station in Singapore, and it was only recently commissioned last year in 2024. And the OGS is located somewhere over here. Let's open up the pointer. It's located about 1.2 kilometers away from the coast. So this is actually a real-time image of Singapore at night from the ISS. And Singapore is a very small country, as I mentioned before, only about 40 kilometers across, but it's very dense and highly metropolitan. So it has a lot of background noise, background light, right? So this is from your street lights and from your buildings and so on and so forth. Now, this places a lot of environmental constraints because all this light actually scatters from the atmosphere, causing our local night to look a lot brighter. So it's higher background counts. So as per our experiments in the past, we show that our mean background count is about 400 counts per second on a 1 milliradian field of view, right? And the nice thing about the SOGS is that it's only located on a university building at NUS, and it's in very close proximity to our labs so that we can form an optical link from the OGS to our labs, right? So these are some of the environmental challenges we have to work with, but this to us makes the most sense because as far as an optical network is concerned, we want the optical ground station to be somewhere in close proximity to facilities and resources that can utilize this quantum network. So the enclosure is just a roll-off design, and within this enclosure, we house, turn off the laser pointer, 1 second, all right. So within this enclosure, we house a 60 centimeter corrected dial Kirkham telescope. So a CDK telescope is similar to a Cassegrain telescope. So there are 2 mirrors, one over here and one over here, and they are co-reflected on one another, and they focus on the Cassegrain focus. So 60 centimeters was the value for the aperture that we have chosen because this number, 60 centimeters, actually optimizes the secret key rate per dollar that you spend on the telescope. So a larger telescope costs more, requires a heavier mount, and then requires more reinforcing. So 60 centimeters was the sweet spot for us. And these mirrors are actually coated on a specialty coating that permits us to have a high reflectivity across a wide and a broad range of wavelengths. So it goes from 600 to 1550. So in the future, we can support experiments in the 780 region. We can support experiments even in the telecom region and even beyond that. So things like thermal imaging using thermal cameras and so on and so forth, right? Okay, so our link budget is as such, right? So we have 20 megacount per second entangled pair production rate with a signal wavelength of 780. So this value was from a previous version where we wanted to use 785, but we have actually since changed it. So 780 nanometer signal wavelength in an 837 nanometer idler wavelength. So this will perform, what the signal wavelength is the one that will be downlinked to the optical ground station, and the idler wavelength will be the one that is processed on board the optical, on board the CubeSat, right? So as per our prediction, we see that a channel loss of about 34, 35 decibels when the elevation is rather low, so somewhere in the range of 30 or so, and it will peak at, or rather it will be the lowest, the channel loss will be the lowest at about 31 decibels when the satellite is directly overhead, so 500 kilometers away. And the secret key rate that we can establish is several kilobits that would contrast quite, or rather would be as per expected, especially when we compare with the Jinan-1 satellite. Right. So the one thing that I want to sort of talk a bit deeper about is how do we reduce noise, and we do that by performing a range of spatial filtering. So how we do that is by having a tiered tracking strategy. So we need a wide field of view image because the initial tracking uses the two-line element, right? So the two-line element, as we mentioned before, gives us an accuracy of about only 2 milliradians. And then we use that to transfer the field of view to a narrower field of view camera. So what this does is effectively spatially filters out the signal to a narrow field of view of 0.14 degrees using a hybrid coarse tracking system, and then a fine stirring system onto the quantum field of view. So the quantum field of view would be the size, or rather would be the field of view of the detector that we have in mind. So all of this leads us to, all of this will lead us to a final tracking accuracy or a final pointing error of about 5 microradians. And that is the limit of what we can do because that is what is limited by the atmosphere, right? So when we do this, we can effectively filter out most of the background noise and isolate the signal from the background, okay? So we have started sort of implementing this, and we have shown some pretty good results. In our case, the field of view that we are targeting is 50 microradians for the coarse tracking and about 5 microradians for the fine tracking, right? And the one thing about Singapore is that makes it a bit difficult to perform experiments as well, is because cloud cover can also impede our ability to track satellites. So we employ a hybrid tracking, hybrid control algorithm such that even under cloud cover, even under sporadic link losses, we can recover the satellite tracking to the required amount, to the field of view for our quantum receivers, right? Then on the back of our telescope, we will also have a quantum information processing unit that we've done it. So this is a base plate that will just sit on the Cassegrain focus of the telescope, and it contains the fast stirring system. So the light will pass through from this full mirror to this fine stirring system down to this dichroic mirror. So part of the light, the dichroic mirror has a fringe at about 800 nanometers, and that light will be used to be imaged on a camera and will be used for fine stirring. And part of the light will also be sampled for the polarization compensation system. So the beacon laser sets the polarization reference, and we use the APDs and a rotatable half-wave plate to optimize for a loop that allows us to maintain the same polarization reference as the satellite. And then the 780 downlink will be passed on to the quantum receiver, which just performs the same measurements in the four bases. So that would be all for the work that we have done and the work that we'll continue to do. So our satellite will be launched hopefully in November of this year, and we can start the integration tests from there. So before I end off, I just want to summarize everything that we have learned before we move on to Q&A. So the main summary, the main thesis of this talk would therefore be that satellite quantum communications have more favorable scaling than optical fiber. And because of that, it acts as a good candidate that allows us to perform quantum key distribution experiments over intercontinental distances without the need for quantum repeaters. And the second summary is the anatomy of the satellite quantum mission. So we learned about weak coherent pulse sources for BB84 protocols and SPDC sources for BBM92, both of which can provably exist in space with sufficient thermal shielding, sufficient radiation shielding, and sufficient decoupling such that it can survive the launch, right? We talked about the wavelength consideration and how will impact the diffraction losses, which dominate, and we talked about the atmospheric transmission window. This also sets us a realistic target for pointing errors that is seeing limited up to 5 microradians, which will change from place to place, but this is the value that most in the literature use. And we talk about the detection parts, right? APDs are far more accessible, but lower detection efficiency, higher duck count rate. But SNSPDs have better detection efficiency, lower duck count rate, but require a substantial infrastructure to enable the cryostat cooling for the SNSPDs. So I think that would be the end of my presentation for now. I will take some time to answer any questions if there are any.
So participants, if there are questions, you can put them in the chat window.
If there's anything that you want me to elaborate a bit further on, because it's a 2-hour lecture on something very interdisciplinary, so there are a lot of things that will be missed out and a lot of things that will be glossed over. So if there's anything that anyone wants me to talk about, I will try my best to answer.
So in that case, could you please, so there are some students who might be masters who are pursuing their post-graduation here, so they would be pursuing master's degree. So probably for them who might be interested in pursuing, let's say, PhD in this particular area. So can you, can you tell the challenges or the research areas which they can focus on in this particular domain?
Okay, so research areas and focus. So in the research of satellite quantum comms, is like I said, very highly interdisciplinary. So it works a lot with optical physics, right? It works a lot on tracking systems and space systems, or space sciences, and it works a lot on avionics, right? So my recommendation is just to have a broad level understanding of everything, right? And focus more on the technologies that allow us to perform satellite QKD, because a lot of the systems that we have are based off of commercial off-the-shelf products, right? And these have existing technological limitations, right? So to sort of talk to understand the best on satellite quantum key distribution or satellite quantum networks, I highly suggest working more on the optical physics side, because that's much more important. And working also on radio frequency studies. So the work on satellite communications have already been very well established, like people who use radio frequencies, and it's typically how the internet was made, way back in the day. So studying that will also be very helpful. Working on that will be very helpful. And as far as satellite quantum key distributions, there are the few universities that I'm aware that are working on this would be CQT, which is us here in Singapore. Germany as well has DLR, has also a satellite QKD network, CUBE, as well as the one big player would be China, which is a bit hard to study in, because geopolitically can be quite difficult to work in China in satellite QKD, just because topic for them. Yeah, I think we have some questions over here. What is the current scenario in India regarding these developments?
Probably you might not be the right person to answer this, but if you want to try, you can try. But I think since Mr. Sheikh is working in Singapore, I'm not aware whether he would be aware of what kind of research is going on in Indian scenario.
Yeah, I'm actually not sure about the satellite quantum comms in India, but I do know that there are some universities in India that are working on terrestrial quantum key distribution. So similar to this, except that instead of linking from a ground station to a satellite, you'll be linking from a place on Earth to another place on Earth using. And that's also an important consideration because at some point, there's also been talks about performing terrestrial QKD links between, let's say, buildings, right? So that is also an area of research that we are working about, the so-called last mile connection. Yeah, I'm afraid I can't comment on Indian satellite quantum comms. I'm just not aware. Sorry about that.
Okay. So next thing is how it will work on satellites. I'm not sure what the participant mean it here. So probably, I mean, you have already shown how QKD will be, I mean, being implemented at various places using the block diagrams. So I'm not sure what this question means here. Probably we can move on to the next question, which is more tougher to realize. Which one is more tougher to realize, uplink, downlink, or satellite to satellite?
So satellite to satellite would be probably the hardest to realize, just because it's difficult to orient satellites. You have very limited controls when it comes to satellites in orbit. So typically for things like the ISS, they have thrusters that allow themselves to orient, but can only point to a certain limit. So inter-satellite quantum links are an important research endeavor that there are a few research groups are working on, but it's still as your question about which is more difficult to realize between uplink and downlink, right? Both of them are equally challenging to realize because they form the basis of the same sort of technology. The only caveat is that uplinks have higher losses, as I mentioned earlier, due to the so-called shower curtain effect. We will get higher channel losses when transmitting from an uplink to a downlink. Furthermore, as a research group, as a facility, we want to support a range of experiments. So it's much more convenient to work on downlink experiments. It's easier to replace detectors in your optical ground station than it is to replace an uplink, just because of the bureaucracies or the red tape, because uplink lasers have certain permits that you have to go through to make sure that they're eye safe for airplanes flying over and so on and so forth. So to your question, both are as about the same level of difficulty, just one of them is much more lossy than the other.
Okay, so the next question is speed and efficiency in terms of quantum and classical data. Any major difference in optical and satellite data transmission?
Oh, that's a very good question. So beyond quantum communications, optical links on satellites are actually a major research area in many universities because classical data transmission using satellites have higher repetition rate than radio frequency ones. So you can actually have gigahertz level communication between the optical ground station and the satellite in classical data. And it also allows us to communicate much further into space. So a lot of research is done into performing optical communications to like distant planets. So for example, Mars, right? Just because of the higher repetition rates of optical links as compared to radio frequency links. As far as quantum data is much more, on a small scale, it's much faster in optical fiber than it is over satellite. And you get higher bit rates when performing over optical distance.
Hello.
Yeah, you see such a major fall off just because of the highly attenuating nature of optical fibers. So I encourage more conversations about ultra low loss fibers that allow us to communicate using an optical network. But thus far, in the current state of technological readiness, quantum satellites are probably the way to go to enable an intercontinental distance. Can
So
we
there
use
is a follow-up question. Existing optical infrastructure can we use for quantum data also?
up to a limit? So there's a point, it's up to a limit. We are attempting to use the optical infrastructure in Singapore, but we are very fortunate because Singapore is very small. So the distance between existing nodes are only limited to a couple, tens of kilometers. So because of the high attenuation of optical fiber, optical infrastructure in the absence of quantum repeaters and quantum memories is probably not possible just using the optical infrastructure, or rather it's very limited. So there are schemes to use the existing optical infrastructure using QKD protocols like twin-field QKD that allow us to perform QKD even under very lossy situations, right? Or even coherent one-way communication as well. So coherent one-way is another scheme that uses coherent light to perform QKD, and that one has your range extended up to about 300 to 400 kilometers last I checked.
Okay. All right. So there are no more questions. So probably we can end this session. So thank you, Mr. Sheikh, for taking your time and making us aware about this topic, which is very relevant to quantum communication, which is the satellite-based quantum communications. And I hope participants have enjoyed the kind of practical demonstration which you have done using the block diagrams for various work which is already going on, I mean, throughout the world. So thank you very much.
Thank you. If there's any existing questions, you can reach out to me by my email. I would like to also acknowledge the team who has worked on this. This is work that is fallen on the back of many people who has, for the past decade, contributed to this research area in our group. So my email is here. You can reach out to me if you want to talk.
Right. Okay. Thank you very much.
Thank you very much for having me.